A legacy data center is defined by its physical constraints, racks of hardware wired together with precise lengths of copper and fiber. In the cloud, connectivity is instant, invisible, and governed entirely by code. For decades, network engineering has been built on physical cables, top-of-rack switches, and Layer 2 VLANs. Those physical constructs form the baseline intuition for how networks operate. An Azure virtual network functions as a software-defined networking abstraction. The entire Azure fabric operates exclusively at Layer 3 and above. It routes based on IP addresses, bypassing traditional hardware layer constraints. Legacy concepts like Layer 2 routing, broadcast MAC addresses, and multicast traffic do not exist in this environment. Applying physical network troubleshooting tactics to an Azure deployment leads to architectural misunderstandings and misdiagnosed connectivity failures. Architecting at an enterprise scale in Azure requires engineers to unlearn physical networking paradigms and master the specific rules of the software-defined fabric. The shift to a software-defined fabric changes the physics of IP allocation within a subnet. On a physical network, an architect provisioning a standard /24 CIDR block expects to lose the network address, the broadcast address, and one IP assigned to the physical router. The Azure fabric automatically consumes exactly 5 IP addresses from every generated subnet. This chart maps a standard /24 subnet. The fabric locks out the IP addresses ending in .0, .1, .2, .3, and .255. 3 match standard physical reservations: network, broadcast, and default gateway. Azure exclusively consumes .2 and .3 for internal DNS. This creates the ICMP paradox. If you send a standard ping to that .1 default gateway to test connectivity, the request will fail. The .1 gateway exists entirely within the fabric's routing logic as a software abstraction. It lacks a physical interface to respond to echo requests. The abstraction extends to how resources join the network. Standard DHCP discovery relies on a Layer 2 broadcast shoutout to the local subnet, a mechanism banned in Azure. Instead, the SDN fabric intercepts DHCP requests directly from the virtual NIC and injects the configuration. Infrastructure components in Azure submit requests directly to an omniscient software layer rather than talking to physical networking appliances. Physical networking assumes that routers naturally pass traffic down a chain of networks. Azure operates on a different logic. In a physical environment, if a valid route exists in the table, the packet moves forward to its next destination. Virtual networks in Azure function as isolated boundaries, making VNet peerings inherently non-transitive. Here, VNet A is peered to VNet B, and B is peered to C. Traffic flows successfully between A and B, but traffic from A attempting to pass through B to reach C is blocked. The fabric drops the packet at the boundary. Establishing connectivity across these gaps requires a hub-and-spoke topology. To achieve transitivity, architects place a centralized routing appliance, like an Azure firewall or a third-party network virtual appliance, directly into the hub network. Deploying a firewall into the hub is only the first step to overriding the fabric's default isolation. A user-defined route, or UDR, sits on the spoke network and explicitly directs traffic bound for VNet C to the hub firewall's internal IP address. The UDR forces the Azure fabric to recognize the firewall as a virtual appliance next hop, successfully bridging the non-transitive gap. Transitivity in the cloud is not a default behavior. It must be explicitly engineered using custom routing logic. Accessing Azure Platform as a Service resources like storage or SQL historically required traversing public endpoints. This legacy model used implicit outbound access, allowing resources inside the virtual network to hit public endpoints via port address translation. To align with modern zero-trust security, Azure is retiring default implicit outbound access, with a target cutoff in September 2025. Secure POS connectivity now requires Azure Private Link. A private endpoint projects a specific service instance directly into your virtual network, assigning it a private IP address and behaving like a local virtual NIC. Cautionary. However, applications face a significant challenge when connecting to this raw internal IP address. Connecting directly to the IP results in a TLS certificate mismatch. The service certificate validates against a fully qualified domain name, and it will reject the raw IP connection. Solving this requires split-brain DNS manipulation, managed through Azure Private DNS integration. When an application queries the public name, the VNet DNS redirects the request to a hidden private link alias. That alias queries the Azure Private DNS zone linked to your virtual network, which outputs the internal private endpoint IP address. The secure connection is successfully established. Securing PaaS access in Azure combines private IP routing with a mandatory, intricate layer of precise DNS orchestration. Maintaining hundreds of user-defined routes and private DNS zones manually introduces significant operational overhead and risk at a global enterprise scale. Managed overlay solutions like Azure Virtual WAN and Azure Virtual Network Manager address this complexity. These abstractions automatically generate transitive mesh and hub-and-spoke topologies across regions based on your high-level requirements. Mastering the cloud network requires assuming strict isolation by default and manually engineering every layer of transitivity. In the cloud, the network is code. IP address spaces and route tables function as explicit logic gates.